Let's move to another module, Generative AI, Functionality, Evolution, and Emerging Trends. Generative AI is a technology that creates new content by learning from large amounts of data. It leverages advanced systems like generative adversarial networks, or GANs, and transformers. We will understand GANs and transformer in next submodule. Generative AI, through these systems, can produce remarkable outputs by understanding and learning from existing data. Using a well-crafted prompt, generative AI will produce results aligned with the provided guidelines or requirements specified in the prompt. GenAI generates text, image, audio, or video content. Imagine teaching a computer to write like a human. That's what GPT-3 does. It learns from a massive amount of text, figuring out grammar and how words fit together. This lets it write articles, emails, or even create stories. It's like having a super smart writing assistant. Imagine teaching a computer to paint. That's what generative adversarial networks, or GANs, do. They learn from thousands of pictures, understanding shapes, colors, and styles. Then they can create entirely new, realistic images from scratch. It's like having a super creative artist at your fingertips. Imagine having a computer that can write its own music. That's what these AI models can do. They learn from countless songs, understanding different styles and rhythms. Then they can create entirely new music, helping artists explore fresh sounds and ideas. There are different categories of generative AI. Generative adversarial networks, GANs, variational autoencoders, VAEs, transformers, and RAG, retrieval augmented generation. GANs consist of two neural networks, the generator and the discriminator, which work against each other. The generator creates data samples, while the discriminator evaluates their authenticity. To understand more clearly, let's make it real. Imagine a game where two players are working together, but they have different goals. The artist is a generator. This player's job is to create fake paintings. The artist tries to make each painting look as real and impressive as possible. The critic is discriminator. This player's job is to spot which paintings are real and which are fake. The critic looks at each painting carefully and decides if it's a genuine masterpiece or just a clever fake. How the game works. The artist starts by creating paintings. At first, these paintings might not look very convincing. The critic then examines these paintings and tells the artist whether the paintings are good enough or if they look too fake. The artist learns from this feedback and tries to improve the paintings. The critic gets better at spotting fakes as it sees more paintings. Over time, both players get better at their tasks. The artist creates more realistic paintings, and the critic becomes more skilled at distinguishing between real and fake. In the end, the artist's paintings can look very close to real masterpieces, and the critic has become an expert in telling the difference. Variational autoencoders, VAEs, are a type of autoencoder that learns to encode input data into a latent space and then decode it back to the original form, introducing slight variations in the output. Imagine trying to describe an elephant to someone who has never seen one. You might start by breaking down the elephant into simpler shapes like circles as head, rectangles as ears, and cylinders as the body and trunk. This is similar to what a VAE does. A VAE takes complex data, like an image of an elephant, and breaks it down into simpler parts or features. Then, it tries to reconstruct the elephant using these features. The key is, it doesn't just copy the original, it can create slightly different versions of the elephant, like one with bigger ears or a smaller tail. This ability to create variations makes VAEs useful for tasks like generating new, similar images or detecting unusual patterns, like an elephant with wings. Transformers are models based on attention mechanisms that excel in processing sequential data, particularly in natural language processing, NLP. Examples: text generation. It can generate coherent and contextually relevant text for applications like chatbots, content creation, and coding assistants. Language translation. Transformers power translation tools like Google Translate by understanding and generating human languages. Transformers understands the whole picture. Imagine trying to translate a sentence like, "The quick brown fox jumps over the lazy dog." Traditional methods might focus on translating each word individually, but transformers are smarter. They look at the entire sentence to understand the meaning. It's like understanding a puzzle by looking at the whole picture, not just one piece. Transformers do this by considering how words relate to each other. Retrieval Augmented Generation, or RAG, is a technique that combines traditional information retrieval with advanced AI generation. Imagine it as a smart assistant that not only generates responses, but also looks up additional information from external sources. This helps provide more accurate and detailed answers. Let's understand the RAG with an example. Imagine you want to write a report on the latest climate change studies. RAG is like having a super smart research assistant that can find all the relevant articles, studies, and data. It then summarizes the key points and helps you write a comprehensive report. It's like having a knowledgeable friend who can quickly gather information and present it in a clear and concise way. Let's take a journey through the evolution of generative AI, highlighting some key milestones. In 2014, generative adversarial networks, or GANs, were introduced, marking a major breakthrough in the field of generative AI. This innovation paved the way for creating realistic images and other media. By 2015, we saw the introduction of deep convolutional GANs, or DGANs, which utilized convolutional layers to significantly enhance image generation quality. This year also marked the founding of OpenAI, a pivotal organization in the advancement of AI technologies. Moving to 2019, Google launched BERT, a model designed to better understand natural language. This year also witnessed Microsoft making a substantial $1 billion investment in OpenAI and the release of OpenAI GPT-2, their first significant language model capable of generating coherent text. In 2020, OpenAI introduced GPT-3, a powerful language model that demonstrated remarkable capabilities in generating human-like text. The year 2021 saw Google announcing MUM, a model with 1,000 times the power of BERT, and OpenAI unveiling DALL, a groundbreaking model capable of generating detailed images from textual descriptions. By 2022, OpenAI launched ChatGPT, quickly amassing over 1 million user signups within a week. Microsoft integrated ChatGPT into Bing, enhancing search results with conversational capabilities. Finally, in 2023, Google launched Bard, leveraging the power of MUM for generative AI applications. They also rolled out a series of experiments, showcasing the potential of AI models in various domains. These milestones highlight the rapid evolution and impact of generative AI, reshaping how we interact with technology and paving the way for innovative applications across industries. Generative AI is evolving rapidly, with constant breakthroughs pushing the boundaries of what's possible. Let's delve into some cutting-edge technologies poised to reshape various industries. Multimodal models are at the forefront of this transformation. These advanced models can process and generate multiple forms of data simultaneously, such as text, images, and audio. This capability opens up exciting new possibilities for creative applications and problem-solving. Imagine an AI that can analyze a scene in a video, generate descriptive text, and create corresponding sound effects, all in real time. Multimodal models enable this kind of integration, leading to richer, more immersive experiences in fields like entertainment, education, and more. They are truly revolutionizing the way we interact with and create contents. Let's explore an example that highlights the capabilities of multimodal models in generative AI. Imagine 3 different prompts given to an AI model. First, the model is shown an image of a horse and asked to provide a description. The AI analyzes the image and generates a detailed text description, capturing the horse's features and surroundings accurately. Next, the model receives a prompt to generate an image of a horse based on a description provided. The AI creates a new image, visualizing the horse as described, demonstrating its ability to turn text into visuals. Finally, the third prompt asks the AI to create a song about horses, complete with a vocal performance. The model not only composes lyrics and music, but also produces a vocal rendition, bringing the song to life. In this example, the AI seamlessly transitions between understanding and generating text, images, and audio, showcasing the incredible versatility of multimodal models. This technology opens up new possibilities for creative expression and problem solving, blending different forms of media in innovative ways. Explainable AI, XAI. As generative AI becomes more complex, understanding how it reaches its conclusions becomes increasingly important. XAI aims to make these models more transparent and interpretable. It helps us understand the why behind an AI's decision. For instance, if an AI denies a loan, XAI can show us which factors led to the decision, like income, debt, or past payments. This transparency is crucial for trust and accountability. It helps us make sure AI is fair and doesn't make biased decisions. Let's understand how XAI works. Imagine a simple diagram that breaks down the process. First, we have training data. This is the foundational information used to teach the AI model how to recognize patterns and make predictions. Next is the AI model itself. Think of it as the brain of the system, processing the data and generating outputs based on what it has learned. Then comes validation performance. This step ensures that the AI is working correctly by testing it with new data to see how well it performs. Interpretability models are crucial. They act like translators, helping us understand why the AI made certain decisions, giving us insights into its thought process. Finally, there's the human element us. As users or stakeholders, we rely on these interpretability models to understand and trust the AI's decisions. In summary, XAI ensures that AI systems are not just black boxes. By providing transparency and making the decision-making process clear, we can build trust and confidence in using these advanced technologies. Let's talk about a technique called reinforcement learning from human feedback, or RLHF. This approach helps train AI models to produce more human-like and aligned outputs by learning from our interactions. Think of it like teaching a child good behavior. You don't just give them rules, you reward good actions and discourage bad ones. RLHF works the same way for AI. We present the AI with different options and guide it by showing which ones are better. Over time, the AI learns to make the choices we prefer, similar to how you'd train a dog with treats. This method makes AI smarter and more in tune with our preferences, making interactions more natural and aligned with human values. Let's use a simple diagram to understand reinforcement learning from human feedback, or RLHF. Imagine the AI agent as a dog we're training with treats. Just like with a dog, we reward the AI for good choices and guide it away from bad ones. In RLHF, we present the AI with different choices. When it picks the right one, we give it a reward. Think of it like a virtual pat on the back. This positive reinforcement helps the AI learn which options are the best over time. It's like teaching a computer to be helpful by encouraging the behaviors we want. The more we guide it, the better it gets at making choices that align with our preferences.